Morning, everyone. So yesterday we started looking at one method to do balancing. When we balance redox reaction, we always want to balance in terms of number of atoms, make sure mass is conserved, no matter has actually poofed out of nowhere or has disappeared. And we also need to balance in terms of total charge, so therefore all the electrons are accounted for. Electrons go from the species that's oxidized, having lost electrons, to the species that's actually reduced. So I'm going to give you just a quick practice here. Again, on a test, they would just ask you to balance. You're more than welcome to do half reaction method, or I'm going to teach you one other method here. Usually I find this method here is a little bit more simple, but people tend to make a little more mistakes. So just depending on which one you're more comfortable, to this day what I do is I try this method first. If I can't do it using oxidation number method, I then switch over to the more systematic brute force half reaction method. So all they're going to ask you is just balance an expression. And in this question here, I want you to balance OCl minus becoming Cl minus and ClO3 minus. Just to throw that twist in here, let's balance it in basic solution. Remember, we would have balanced with H pluses. We would just balance everything in acidic first, and then there was just that one little twist at the really end if need be. Okay. This question here is a little bit more interesting because normally what you would do, thinking about your half reaction method, I want to break up two half equations. Usually I have two things becoming two things, right? In this question, we actually have OCl minus. The OCl minus, when it becomes Cl minus, it does one reaction. That very same OCl minus here, as it actually becomes ClO3 minus, it actually does something different. There's a special name we give to these reactions here. This is actually called the disproportionation reaction. Disproportionation. Essentially, my reactant is sort of split personality here. It's one species undergoes both oxidation and reduction. One species gains and loses electrons, right? Just to make things easy, right? If I have undergone an oxidation, let's say, it's not those very same particles that undergo reduction. So what you can do here for simplicity is you can pretend, well, let's just write the OCl minus twice. It's still the same chemical, OCl minus, but then we can track a little bit easier. Maybe when OCl minus becomes that's one half equation. Maybe when my other OCl minuses become Cl minus, this is another equation. You'll notice these guys here are the same equation, same reactant. So let's follow through our methods here. Let me just hint at what you're going to do. So half reaction method, first step, we're going to break up the two half equations. Okay, that's always the first step because it's too hard to balance all at once by inspection. So let's do, what if OCl minus ends up becoming Cl minus? And what if my sort of copied OCl minus becomes ClO3 minus? It is still disproportionation. It is still one chemical actually splitting off and then becoming two. Once you broke up the two half equations, we're going to balance in terms of major hydroxide. So that's going to be just a nice memory aid for yourself. We balance our major atoms, everything that is not O or H. We're going to balance our oxygens by adding water. We're going to balance our hydrogens by adding H+, even though we would be basic. And then we're going to balance our charges by adding electrons. That just allows you to balance each half equation separately. So let's just do some practice here. My first expression here, my major atoms would be chlorine, 1 chlorine, 1 chlorine, 1 chlorine, 1 chlorine, we're good. How about the oxygens? I have one oxygen on the left, no oxygens on the right, so for the red equation, I'm going to add 1 water to the right-hand side. That makes sure I have 1 oxygen, 1 oxygen. On the green equation here, I have 1 oxygen. I already have 3 oxygens, so I'm just going to add 2 waters to the left-hand side. Right? That's going to end up having 2 times 1 oxygen is 2. Plus that 1, I have 3 oxygens. I have 3 oxygens. At least the number of O's are accounted for. I haven't worried about charge because charge gets balanced at the really end. At first, I really didn't have any H's, but it's because I actually added water. Most of these solutions take place in aqueous. Now I've actually screwed up the number of H's. I now have 2 H's, no H's yet. I'm going to add 2 H pluses on the left side. On the green equation here, I have 2 times 2, so 4 H's, no other H's here, so I'm going to add 4 H plus. Again, there's no guarantee, having added water to one side, you have to add H plus to the other side. You just match up based on the half equation you're given. And then finally, I still have no clue who's oxidized or who's reduced. What we're going to do is we're going to add electrons. As you add electrons, you add it to the side that has a higher total charge, and the total charge is going to steadily come downwards. So what's the total charge on the left side here? Every proton here is +1. There's 2 of them. +2 minus this one here. Total charge of +1. The total charge on this side, because of the chloride, is actually -1. I'm going to add 2 electrons to the left-hand equation. The green equation here, my total charge here is actually -1. On the right-hand side, I had a -1, but I have 4 positive ones here. Total charge there would actually be a +3. +3, I need to add 4 electrons, and that would end up knocking +3 down to -1, and -1 would match -1. So we just want the total charge to match left side and right side. Neither of them have to actually equal to 0. At this point here, we have balanced the half equations. We're balanced in terms of number, we're balanced in terms of charges. Because this first half equation here has electrons on the left side, we know that involves a reduction equation. The reactant that was involved there, OCl minus here, upon getting reduced, it goes to Cl minus. If the electrons are on the right-hand side, we know it's actually an oxidation reaction. Those same OCl minus, it was a disproportionation after all. As they lost electrons, as they pass electrons over, as they become ClO3 minus, these electrons actually pass over to OCl minus. In the half equations, you're more than welcome to have electrons, right? We are going to 1 part gain, 1 part lose electrons. As I get back to the whole equation, as I combine them together, I want to make sure that there's no free-floating electrons. So how we're going to do this here is we're going to do lowest common multiple between 2 and 4. Well, both 2 and 4 go into 4. Let's take the equation that ends up doing just 2, and what I'm going to do is I'm going to multiply that by 2. That way I've set it up. 2 times 2 make 4 electrons. The 4 electrons cancels these 4 here, and therefore the rest of it would cancel out. Everything that's involved in this first expression has to be multiplied by 2. So 2 times 2 ends up giving you 4H plus. 2 times the OCl minus, 2 OCl minus. I'm also going to copy down the 2 water and the OCl minus from the second equation. All of these at the end of the day are reactants. All of these are products. On the right-hand side here, the first equation scales in that 2 there. So 2 chloride and 2 waters. The other expression here we're going to get is ClO3 minus and 4H plus. Okay. At that point there, everything should be balanced. We had balanced the 2 halves, and now we've actually set it up. Notice that there are no free electrons in nature. Because we had balanced the half equation separately, adding H pluses and adding waters, there's a good chance that I may have similar terms on both sides. In fact, this time it works out really nicely. 4H plus on the left, 4H plus on the right. Let's just cancel both. I have 2 waters on the left, 2 waters on the right. Let's just cancel both. We saw last day if the numbers don't quite match, let's say I have 5 waters and 2 waters, I can still cancel the 2, but that still have a remnant of how much water there is. Being a disproportionation reaction, we were looking at the same chemical anyways. I have 2 OCl minus and 1 OCl minus. In total, that means I have 3 OCl minus. As that becomes 2 Cl minus and ClO3 minus, this should be balanced in terms of number and charge. Let's just check it for ourselves here. I have 1 oxygen, 1 oxygen in each molecule times 3, so 3 oxygens, 3 oxygens. 3 times chlorine means 3 Cls, 2 chlorines there, 1 chlorine there, so 3 Cls. Total charge is 3 times negative, so minus 3. 2 negative there with the -1 here. We're balanced for charge and for atom. Notice in this situation, I also asked you to balance for basic. We had done everything balanced for acidic. Normally, if I did have extra H pluses over, that's when I would add hydroxides to kill off the H pluses. This time, I don't have any H pluses, so this solution would already actually be balanced for basic. As you take a step back here, you might end up realizing, oh, I could have guessed that. I could have had OCl minus. I could have said, well, I have, I need 3 O's. I need to put a 3 here, 3 chlorines. Oh, I then put a 2 here. You probably could have guessed it, but that's only because it was a very, very simple expression. I'm still teaching you a half reaction method. Even for a much harder equation, you can still follow this half reaction method. Very tedious, but very systematic. Okay. Today what we're going to do is we're going to switch over and we're going to learn something referred to as oxidation number method. So again, just another technique of balancing. Let's balance using oxidation numbers. Those fake charges that we had introduced a couple of days ago. Okay, so oxidation number method, just let me give you a gist before we go through the details. Oxidation number method, first step, I want you to assign the oxidation numbers, find all the oxidation states. That's why we got a lot of practice for the first class here. Just see if you can identify those charges, follow through your rules. Because if I have a chemical where the oxidation number actually increases, for my charge to roughly go up, I would have to lose electrons. Oxidation number increases actually means an oxidation. While if your oxidation number actually decreases, it actually is a reduction. All right. You can translate that for yourself. Leo the Lion says, oxidation is a loss of electrons. That means my charge can go up. Reduction usually means I lose stuff, but in this case here, I'm actually gaining negative things for my charge to actually come downwards. Okay, and it's always the reactants that are involved for this. Okay, what we're going to do, earlier we had done this sort of major hydroxide. That's sort of ordering in balancing a half equation. What oxidation number method does, we still balance the major atoms. That's always going to be just by inspection. What we're going to do in step number 2 is we're actually going to balance the charges first, even before we balance the oxygens and hydrogens. So what we're going to do is we're going to match up the changes in oxidation number. That would effectively balance the charges for you. And then the third step here seems really familiar. The third step, we're going to balance the oxygens by adding water. We've done that before. And balance the hydrogens by adding H+. Now, what's not immediately obvious here, if you compare sort of this sequence, what's different about half reaction method, you notice I'm actually not breaking the two halves. I'm actually keeping the equation just all in one. I'm not breaking up the bits, balancing the bits, and then putting that back together. So in general, this would be a little bit more simple. So let's just practice through an oxidation number method. Again, they're just going to ask you to balance. You're more than welcome to do half reaction method if you're comfortable with it, or you can do oxidation number method. I generally find people make a few more mistakes with oxidation number method, but as long as you're careful, you should be okay. Right? So I gave you this redox equation. I have two things becoming two things. Half reaction method would have involved, let's break up the two parts. Probably the phosphorus looking compound goes into the phosphorus compound, the tellurium compound and tellurium compound. Sure. For oxidation number method, I don't have to do that. And in fact, if this were a multiple choice question, if it just said, oh, who gets oxidized, who gets reduced, don't bother doing balancing. Balancing is a lot of work. Only balance if they ask you to balance. So in this question here, let's just have a look. Let's find the oxidation numbers of absolutely everything. Let's go through our list of rules. Let's pretend things are ionic, and let's assign it the charges. This is tellurium here in the elemental state, so 0. We have H is usually +1. Oxygen is usually -2. 2 H's gives you +2. 2 times negative gives you -4. These have to give you an overall -1. So 2 minus 4 is a -2. Something -2 has to give you a -1. The phosphorus is sort of like in a +1 state. I want you to get enough practice that without actually showing the algebra, you can do it by inspection like that. How about the TeO4 minus? Again, the oxygen is usually -2. There's 4 of them, that gives you a -8. Tellurium minus these 8 here have to give you a -2. The tellurium has to be kind of like a +6. Not actually a real charge, but if this number here ends up going up, I know oxidize. If this number goes down, I know reduction. How about the phosphate? Phosphate here is a polyatomic, it actually is covalent. Let's just pretend it's ionic for now. Every oxygen is -2, there's 4 of them, -8. Something -8 has to give you -3. The phosphorus here is actually +5. Okay. Up to this point, we haven't actually seen an oxidation number that's fractional as well, but it's totally okay if it's fractional. They aren't real charges anyways. You just want to track the change. Okay. So if the question were merely asking me who's oxidized, who's reduced, again, the emphasis is I'm only looking at the reactant side. Okay. If my oxidation number goes up, it's been oxidized. So for example, my phosphorus has gone from sort of like a 1, later on it's a 5. My oxidation number has actually gone up by 4. If the change is positive, I know this is an oxidation reaction. The reactant that was involved is the chemical that was oxidized. It's the phosphorus in this H2PO2 compound that actually is oxidized. That should mean that the other guy is reduced. The tellurium goes from a +6 down to a 0. The change here is actually a -6. Because that one there is a minus, we know it's a reduction. The reactant that was involved is the chemical that was reduced. So again, if the question were just merely asking who gained electrons, who lost electrons, I've already answered that problem. Only balance if they ask you to balance. Okay. So let's try through. They are asking us to balance here. Just before we match our oxidation numbers, let's make sure that the major atoms are accounted for. Things that are not O or not H, make sure they're the same number. I have 1p, 1p, good. 1Te, 1Te, good. Okay, my major atoms are currently balanced. What I'm going to do now is I'm actually going to match up the change in oxidation number. The change at the end of the day, this one sort of means a lose of 4 electrons. This one sort of means a gain of 6 electrons. Just like we did lowest common multiple to make sure the electrons end up canceling, you want to do lowest common multiple between these changes. What do 4 and 6 both go into? Well, they both go into 12. So if I take this expression here, everything involved in the reduction, if I scale it up by 2, that would end up being a negative 12. I would need to scale this equation up by 3. That would end up giving you a plus 12, because plus 12 cancels a negative 12. That should then cancel out. So everything that's involved in these changes, so from H2PO2 becoming PO4, that was a change of plus 4. Let's multiply it by 3. Had I had a coefficient before, let's say there was a 5 beforehand, as I scale up by 3, sure, go 3 times 5. Okay, so that's why it's important to balance your major atoms first. In this equation, everything was just 1 to 1 here. Let's just multiply by 3. So 3 times the H2PO2 minus, the other expression has to be scaled up by 2. I only had one of them to begin with, so let's add twice a tellurium compound, 2TeO4 minus 2. This one here ends up giving you 3 PO4. Color code it for you here. And then we have 2 tellurium. All right. Again, I want to emphasize here, it's not immediately obvious. I have not broken up half equations. This is still the entire redox equation. Okay. But somehow by doing that, the charges are now balanced. If I check the charges down, I say, wait a second, they're not balanced. 3 minus and 2 times negative 2 is negative 4. That's like a negative 7, and yet here it's negative 9. I'm saying somewhere behind the scenes, the electrons would cancel out. I'm not done yet, because I still have step number 3. I still need to make sure the oxygens are balanced by adding waters, balance the hydrogens by adding H+. Because I'm doing this to the whole equation, I'm not going to end up with a situation, oh, I happen to have H+ on the left side and right side, and now they need to cancel out. This is just overall. So let's try it out here. Let's balance the oxygens. How many total oxygens do I have on the left side? Every compound here has 2 oxygens. I have 3 of them. 3 times 2 makes 6 oxygens. I have 2 times 4 make 8 oxygens. 6 plus 8, I have 14 O's on the left side. On the right side, I have 3 times 4, that's 12. I'm going to then add 2 waters to the right-hand side. Okay? I'm just balancing for the number of oxygen atoms. I don't care about the charge. Then we want to add H's to make sure those balance as well. I have 2 times 2, so 4 H's. In this case here, I have no H's yet, so 3 times 2, I have 6 H's. 6 H's and 4 H's. Again, here's an example where, oh, I added water to one side. Actually, I still need more H's, because this one here had so many H's, I need to add 2 H+. At that point, when you've added the water to balance the oxygens, added the H+ to balance the hydrogens, everything should be cancelled out. And now we see that it actually is balanced. If you check the charge again, with the minus 3 and the minus 4 there, minus 7 overall, I had minus 9, but plus these 2 here, it's minus 7. We had already worked out the electrons behind the scenes. The electrons don't appear in the overall, but they definitely do cancel out. So hopefully you see the benefit in this one here. It's a lot shorter because I'm not actually having to break up the 2 equations, and I'm actually, when I'm adding the waters and adding the H+, I can just add it directly to the overall redox expression. This, again, it has been balanced. If they don't specify, you can assume it's acidic. If they specify it's acidic, just that's it. It's acidic. We have an excess of H+, so be it. If they say basic, do this step here, and at the really last step, then add the hydroxides or add that self-ionization of water to end up canceling it out. Okay. Now, why do I say people tend to make more mistakes with this? Okay. I'm going to give you another example here. Let's do SO3 minus 2. Cr2O7 minus 2 ends up becoming SO4 minus 2 and 2 Cr plus 3. Sure, we'll do this one here again in basic, just in case we need to do that one added step at the really end. Okay. First thing, don't forget to balance your major atoms. And this is actually where people end up making mistakes. Sorry, I didn't have that 2 yet. But basically, the major atoms here, I have 1 sulfur, good. I have 2 chromiums, I have 1 chromium there. I want to put a 2 right away. I could care less what the charges are. Okay, Now, we don't really see, well, what's the big deal, right? Balanced major atoms, I'm used to doing that, okay? What's the next step? Again, they're just going to say balance. We're going to try using oxidation number method. Let's try finding the oxidation numbers of absolutely everything in this equation. So let's go through with some practice here. The oxygen is usually -2. 3 times -2 is -6. Something -6 gives you -2. The sulfur is like a +4. For the Cr2O7 compound here, the O7 here is a -2. There's 7 of them, -14. 2 times chromium minus the 14 has to give you a -2. The 2 chromiums have to give you a +12. Each chromium would have to be a +6. I want you to remind you that oxidation number or oxidation state is per atom. Okay. That's important for this one here. So sure, I actually have 2 chromiums. So this Cr is +3, this Cr is +3. If I say, well, what's the charge of just this one atom? Well, that's +3. The other one happens to also be +3. We'll do that in a little more detail in a second here. And the SO4 -2 here, the oxygen here is -2. There's 4 of them. That ends up giving you a -8. Per atom, the sulfur is actually a +6. Right? Again, if the question we're just asking you purely identifying your agents, who's the oxidizing agent, who's the reducing agent here? The oxidizing agent helps something else get oxidized. It helps someone else, its oxidation number to go up. You'll notice that going from sulfur being 4 to 6, that's going up. That means the reactant, the SO3 was oxidized. That therefore means the chromate here, dichromate, Cr2O7, is actually the oxidizing agent. As an agent, it is present to help someone else oxidize. It itself ends up getting reduced. Okay? The other one I would expect to be a decrease, which it does. The chromium goes from like a +6 down to a +3. So that's going to be a drop by 3. Because that's a decrease, the reactant that was involved is reduced, and therefore that makes the SO3 -2 the reducing agent. So we can already do a lot of questions just identifying, just labeling who gets oxidized and who gets reduced. Here's the problem that people make. Because oxidation number is per atom, I already happen to have 2 chromium major atoms. So let me just draw this out for you. My dichromate, I don't know exactly what it looks like. It's 2 chromiums, and I have 7 of these oxygens somehow bonded. Right? Because oxidation number is per atom, each of these chromiums is +6. So when we did a change, yeah, it's sort of like chromium dropping from 6 to 3. In fact, this first chromium drops from 6 down to 3. That already is a -3. But what about the other chromium? It also goes from +6 down to -3. Because I actually have 2 chromiums actually undergoing the change, I actually want to change this to a -6. Let me write that down in words here. We have 2 chromiums changing from Cr being a +6 to Cr being a +3. So therefore, this would in total need to add a net of 6 electrons. This isn't a lowest common multiple yet. I haven't tried to match up, okay, who's oxidized and who's reduced. This is just purely, I happen to have 2 of the major atom. Each major atom goes from 6 to 3. That change here is already a -6. So that's the part that people miss. Balance for major atoms, depending on how many atoms are undergoing that change, that might already scale up this change. And then finally, you do the lowest common multiple step. So now that everything is accounted for, both chromiums here would net a -6 change. The SO3 minus only does a +2. What's the lowest common multiple? This time not between 2 and 3, but between 2 and 6. It still is 6. So what I want to do is everything involved in this +2, I want to scale it up by 3. So that's going to be the sulfite and the sulfate equation. I'm going to put 3's in front of those ones. So let's just copy this out here. We have 3 SO3 minus 2 dichromate. Ends up giving you 3 SO4 minus 2. And at this point here, somewhere behind the scenes, the electrons have canceled out. That's why I don't have any free electrons here. Remember, it's not fully balanced yet until I actually add the waters to match up the O's, add the H pluses to match up the H's. So let's try it out here. Again, this is the entire redox equation. This is not broken up yet. Okay. I have 3 times 3, so 9 oxygens, plus the 7 here. I have 16 oxygens on the left-hand side. On the right side, I have 3 times 4, so 12. I would then need to add 4 waters to the right-hand side. That makes sure I have 16 O's and 16 O's. And then looking at the number of H's, well, I have no H's on the left. On the right-hand side, now I have 8 H's. At this point, when I actually add the H pluses, everything should be balanced. Again, I usually run out of time for this here, so I just basically, let's add up the charges. If the total charges match up, we're probably good. Every proton is plus 1. 8 of them gives you a positive 8. 3 times negative 2 is the negative 6. So 8 minus 6 gives you a positive 2. Minus these 2 gives you no overall charge. On this side here, 3 times negative 2, negative 6. 2 times positive 3 gives you positive 6. Again, no overall charge. If the charge is balanced, we're probably good. Okay. Now, one last step here. Really, really elegant here because I'm not having to break up half equations, but so far I've still been assuming acidic. We still need to add this one last step because they had told me I want you to balance in basic. It's just one added step. I don't have an excessive H plus around. What I want you to do is I want you to add enough OH minuses. What you do to one side, you have to do to the other. Add 8 OH minuses. In some sense, yes, the H plus and the OH minus, they cancel out. Acid neutralizes base, but it's not like they vanish. They end up creating 8 waters. And now I'm going to probably have waters on both sides, which I do. 4 waters there, 8 waters there. Let's cancel 4 of these and get rid of that. And then finally, the relative order doesn't matter. I can have water first. More importantly here is you have the correct coefficients. So balancing, very tedious in this section, but it's very, very systematic. It's not just by inspection. We have to end up adding waters, adding H pluses to actually do this balancing. Okay. At this point here, everything should be balanced. It is in basic solution because we have a net of hydroxide as opposed to acid. Okay. So see which method you like better. Again, for the practice, they might say practice balancing using half reaction method, practice using oxidation number method. On an exam, they just say balance. Totally up to you which one to balance with. Okay. So what I'm going to do here is I'm going to work you through one more equation here. The nice thing about these problems here is you can always tell whether you're right or not. Right? If we're balanced for number and we're balanced for charge, we know we have the correct answer. Okay. So let's just start off with this expression. Let's try to balance it using oxidation number method. First thing to do, make sure your major atoms are balanced. That's the part that people always miss. Okay. So we have 1 selenium good, 1 iodine, 2 iodines. Oh, already I need to put a 2 either. Let's put all the oxidation numbers. So every oxygen here is negative 2 times 3, negative 6. Selenium is like a plus 4. Going down to selenium elemental, that's a hint that this one here is probably a redox equation going from a compound to the atomic state, neutral. This one here is actually a drop by 4. Whenever oxidation number goes down, the chemical involved has been reduced. Okay. How about the I minus? Per I minus, so I actually happen to have 2 of them, but per each of these i's, it's like each I is actually a negative 1. The I here in the elemental state here is 0. So it is going to be I2, it is going to be diatomic. Overall, we're neutral. That's like saying this is 0 and this is 0. Because even though the change here ends up going up, negative 1 becomes 0, I've gained by 1. I know this chemical has been oxidized. But because I have 2 of these major atoms doing this change, this one goes up by 1, this one goes up by 1, this one here is already a net change of plus 2. Okay? Even before you do lowest common multiple. It's just because I have 2 major atoms of I that actually end up undergoing this plus 1 of a gain. Then I do lowest common multiple. Then I go, what do 2 and 4 both go into? They both go into 4. Let's take this equation and then let's multiply by 2. So everything that's involved in this expression, the I minus and I2, gets further scaled up by 2. I already had a 2, so you now go 2 times 2, so that's going to be 4, and I'm going to have 2I2 there. Somehow behind the scenes, that one would have balanced the electrons. And at this point here, you would end up adding waters to end up balancing O's, add H plus to end up balancing H's. Because they do not specify acidic or basic, I'm going to assume acidic. Okay. So let's match it up here. I have 3 oxygens, no oxygens here. So let's add 3 waters to the right. And then now I've screwed up the number of H's. So I have 3 times 2, 6 H's, no H's there. At this point here, if I add 6 H pluses, it should all be balanced. If you're running out of time, just check your charges again. 6 times positive 1 is positive 6. Minus the 2 minus these 4 here is going to be minus 6. So it's going to be 0 and 0. We're going to be cancelled overall. Okay, and there I know I have the correct answer. Okay, So this balancing here just takes practice. Totally up to you whether you use half reaction or oxidation number method. Usually I find oxidation number method is more of a shortcut, but also more error prone because people tend to forget they have to scale it up based on how many major atoms are doing the change. Okay? Let me know if you have any questions. Thanks, guys.